Welcome back. I'm René. I work for Bridge Diagnostic in Boulder, Colorado. In this session, we're going to look into sliding FFTs. From our previous test, the rainflow test, we have data displayed here. And we can run from this page, we can run FFTs. And we're going to do that. An FFT, the fast Fourier transform, is a transform of your time record, and the time record here on my bottom display is limited between my two cursors. So all the data in between my cursors is used for my time record. And you see that the FFT is not a really nice result. Let's have a closer look what we're doing here. I set the x-axis to 2 to 10 Hertz. We can do that in the settings file. So the settings, x-axis is frequency, the maximum is 10, the minimum is 2, and the mapping is linear. For the magnitude, we use a maximum of 10 dBs and a minimum of minus 60 dBs. The axis mapping is in dBs. dBs is very common for electronics engineers, and it basically means the 20 times the logarithm, 10 base logarithm of the number. And that gives us a large range to look at signals. So, just a refresher, if we say 0 dB level, which means 1, that is the amplitude of the signal is 1 micro E here. Minus 60 dB would be 3 times 20 dB, which means that, and 20 dB is a factor of 10. So if you divide the number minus 60 by 20, you get minus 3. That means this is 10 to the minus 3. But 10 to the minus 3 on a linear scale is very difficult to see. On a logarithmic scale, it's much easier to see. And we want to see what the resonance frequencies are doing. So we set it up in this fashion. And now we can look what the frequency does. Let me zoom in on our frequencies and go to a resonance. And here we can see that we have at 6.2 Hertz, we have a resonance. But you can also see that we only have a few points. We cannot accurately determine what the resonance frequency is. The resolution of an FFT is basically 1 over the period of time you do the FFT over. So, and the length of time is here determined by my two cursors. If I want a higher resolution, I have to take a bigger time record. So let's make the time record larger. And you see that my resolution is increasing. But something else happens also. You see that the FFT gets quite confusing. We have now a higher resolution. As you can see, I can now accurately determine where we are. Let's put my cursor here. But you see that I have different resonances in my peaks. And that is a problem when we are going to look at FFTs. We want to see with high resolution what the resonance was. Okay, we can do that, but the resolution is now too low. If we make the time record longer, we get a better resolution. But there is not much frequency information there, so the magnitude is dropping. If we include other resonances, these resonances are not in phase because the system started to resonate, damped out, and then a new event started it. But it doesn't mean that the phase of the second event, if we look at this block here, the second event was in phase with the first event. In worst case situations, you can have that a resonance frequency starts, and then the next time we get a resonance, it is exactly in counter phase. You run an FFT over this area, and the first resonance is cancelled by the second resonance. You have to keep these things in mind when we start setting up FFTs and sliding FFTs. We want to have large records but we also want to have a high resolution. And it doesn't come together that easy. It depends. Enough about that. This is a function you have also available on STS Live. We're going to set up the test. By now you're familiar with all this. Demo. And here we see a page, but we will slow down the simulation speed somewhat. This page is intended to help you out setting the proper parameters. We have quite a lot of parameters to do a sliding FFT. What exactly is a sliding FFT? We're setting it up in the buffer page. We have a circular buffer size of 20 seconds. Here you see my circular buffer of 20 seconds. It plots it up to 22. But this is a 20-second buffer. I can make that buffer larger. And we've seen in the previous that if I have a bigger buffer, like 100 seconds, my resolution of the FFT will be better. The buffer is filling up. The output to the FFT is set to 5 seconds, which means that every 5 seconds this buffer is sent to an FFT routine. So the record length sent to the FFT is 0 to 100 seconds, and then 5 to 105, 10 to 110, and so on. We can set up a filter on the raw data. So the data comes in and is filtered by this filter block. The output of the filter is demonstrated here. If the filter is set too low, your data will disappear. If the filter is set too high, the filter is basically inactive. The filter can never be set at a higher frequency than half your sample rate. So let's put this back on 10. And we can set the order of the filter also. Adding a filter for an FFT has limited functionality. Some people like to do it, but an FFT basically does the processing over the same data. And if you do the filter, you will see that you will lose the high frequency information. But you can also take the FFT and ignore the high frequency information. So the next step we already looked at, it's the buffer set to 100 seconds here, and we output it to the FFT every 5 seconds. I have the result of the FFT here. Let me put this. Disable auto scale and zoom in on my FFT data. And here we see what we also discussed previously. We see a very strong peak, and we see some very small components from the other trace. So let's have a look what that is. If we go to the simulation page, you can see that we have a simulated frequency of 2 Hz, which matches our result here. And we have some noise ratio, increasing the noise floor. But we have 2 signals. One is the continuous signal, the black trace, and one signal is a modulated signal. And the modulation is such that the signal resonates in phase and in counter phase. So if we take an FFT over this record, the in phase and in counter phase and then here we have basically eliminates that signal. The FFT is null, and we see that we have a very small peak. We can disable the main plot. You see that, and you see that we have some peaks over the mean. We would call that sidebands in the electronic domain. We have a vibrating system. But the original frequency of 2 Hz is completely gone. That completes my demonstration of rainflow. Thank you for your attention. So when we change the frequency, we will see that it shifts up. To do that, I have to reset my buffers, turn my auto scale on, and we will see that the peak shows up here once we reach the 100-second buffer. So let's speed it up, the simulation. And there the data is coming in. And we are now centered around 5 Hertz. But every 5 seconds, the FFT will carry out again and the plot resets. So if we turn autoscale off, we don't have that issue. The output of the FFT is sent to a binning routine. So here's the setting of the FFT. This is standard Windows. The window means that the incoming data record, let's say that our data record here is 0 to 100 seconds, is filtered by a window. And the window is needed to basically make ends meet for an FFT. An FFT is a circular integral over your data pattern. That means that the 0 point here has to match the 100-second point. And what we do then is first put a window over it, which multiplies this time record with a window which is always null at the beginning and always null at the end. And in between it can have a certain shape. So what you will see after the window is a null signal at the beginning and a null signal at the end. In that case, you can say that the signal is periodic because we start with a null, we end with a null, and you can imagine that the same signal repeats itself. We have averaging modes. We can average the FFT before passing it to binning. We can have different weightings for the averaging, and we can say how many averages the FFT should make before it passes to the binning. For now, we just keep it with the default settings. Let's go to the binning page. We can select how many bins we want. The binning can be handy because you can zoom in on a certain spectrum of the FFT. We know that our resonance frequency will be at around 5 Hertz, and we simply want to see only that frequency area in that range. So let's say that our start frequency is only 2 Hertz, and we want to see from 2 Hertz to 8 Hertz, so 5 Hertz plus 3 and minus 3. That means that if we have 50 bins and we have a span of 6 Hertz, that our resolution should be 0.12. And my stop frequency is now 8 Hertz. This is an indicator. You cannot change it here. You have to change it here. Let's do 100 bins so we get some nice resolution. Now you see my stop frequency is 14 Hertz, but I can reduce that because I want to have a higher resolution here. I cannot make a higher resolution than my original FFT. And my FFT is taken over a period of 100 seconds. So my resolution of the FFT will be 1/100th of a second. So that resolution can be obtained. If you would make the binning less than that, it still will bin the data, but basically it doesn't help you. I think we're set up here. We can see how the binning operates now. We have a peak hold, and we can see plot 1 is binning, and plot 2 is also binning with the sidebands. And we have quite a resolution compared with the original FFT. We can select cumulate, and then the binning will cumulate as long as we measure it until we save to file. If my save interval is 30 minutes, then every 30 minutes we save to file and the binning will be reset. We can simulate that by speeding things up, and you will see that we keep cumulating until it resets when we save it to file. I jumped forward and the binning has been reset. 30 minutes was a little bit too long for a simulation. If we are satisfied with our settings, we can Let me slow down the simulation speed. We're satisfying with our settings. We can start and save this as a test specification. Part of the test specification is only the filter settings, the buffers, the FFT parameters, and the binning parameters. Well, let's go and add some sensors. Our famous 3 sensors. And we have specified the sliding FFT parameters. You see, the number of parameters is quite large, and they have to be precise. Typos will not be appreciated by the core. So please use this editor to set up these parameters so we will not have any confusion there. We're done, and we can start test. But the FFT will not be displayed. Nothing is happening here. And I'm going to stop the video for a moment and collect the data, and then we can look at what actually is saved to the TDMS file. I continued the test for approximately 10 minutes. I'm going now to stop the test. And let's look what data we collected. You see here the FFT binning demo. Open it up in Excel. You can check out the metadata. The metadata has all the parameters we configured it. You can also see that I made a change. The binning save interval is set to 60 seconds. It was 30 minutes, but that would take a long time. So I changed it to 60 seconds to get some records. Each amplifier of each sensor has now its own spreadsheet. And we can see that, for instance, amplifiers 4, we have records, frequency records, with a timestamp. And they were saved every 60 seconds. You can open them up, insert, let's see, and make that bigger. We can see that when I activated the resonance, we have high resonance peaks accumulating, but we have many records, but we have hardly any resonance frequency. And please note that this is a linear scale. If we would change that to a logarithmic scale, let's see, we can see that we have now on a logarithmic scale, if there is no excitation at all, we just have a very small noise amplitude, and here we see some excitation, that the system was excited. This completes my demonstration of sliding FFTs. Thank you for your attention.